Morning and welcome back to the course. We're in the middle of talking about phosphorylation-dephosphorylation reactions. We're using this ubiquitous biochemical process as a means to discuss really the nature of life as defiance and specifically the notion of the ATP Biological Battery. I was remiss in not having introduced the paper that really has inspired me. And that's from Hong Chen, who's a professor at the University of Washington. And I think I just want to say that over the last 20 years, this guy has been on a really brilliant rampage, as have others. You know, there's people like Udo Seifert and others. I'm not going to say more about that right now, but a rampage which has attempted to recognize that biological processes are often in non-equilibrium steady states. That's point one. And they're also isothermal. And so anyway, I mainly just wanted to call this paper to your attention, call Hong Chen to your attention more generally. What I would say is that the guy is very deep. And, you know, in addition to being quite good at biophysics, he's also an applied mathematician. And so, you know, sometimes I find that his work is a little bit over my head, but often the effort put in is rewarded. So anyway, I just wanted to make sure that I brought that up. So where are we? We talked last time about the idea of the enzyme shown here as E being phosphorylated, and the reaction that performs that phosphorylation is shown up here. And then the dephosphorylation reaction is shown down here. And the point that we made last time was that detailed balance is broken, that there is a net flux around this loop. In other words, things travel to the right on top and then back on the left. And every single time that every single time that a phosphorylation-dephosphorylation reaction takes place, then there's a free energy cost shown down here, which is the free energy cost of the use of the ATP biological battery. And what we're going to do in this vignette, in fact, is to go through the details of that free energy cost. So the thing that came out of our last analysis was this idea of working out the flux. So, you know, if you recall, we wrote down the relevant chemical reaction. That led us in turn to a dynamical equation. So this is telling us the rate of change of the amount of E and the amount of E star. We noted that in steady state, which I think is the right picture often for us to be thinking about. We're in this non-equilibrium steady state. We could find the values of E and E star in that steady state, which we did. They're shown here in this box. The analysis, you know, just as a reminder, we had two equations and two unknowns. Equation number one was the dynamical equation itself, which here we set equal to 0. And the second one was the constraint equation, which is the total amount of enzyme is constant, shown as E tot here. And so if I get rid of an E, I must therefore have produced an E star. So using this constraint equation, we basically eliminated E star from the steady state equation, and that permitted us to solve for E in steady state. And that's this result. We similarly found E star. And once we have those, we can compute, as you see here, we can compute the net flux. That is the amount going to the right minus the amount going to the left. We made this observation, very interesting observation, that this numerator tells us about the flux. And hence, when the driving force is 0, that corresponds to being in equilibrium. That means that this numerator is 0, which tells us, you know, no net flux given by this condition or this business. Okay, you know, so that's very cool, I guess, is what I would say, is that gave us a sense of how the drive is basically the out of equilibrium character of the ATP to ADP ratio. And now what I want to do is I want to evaluate the cost I want to think about the fact that there is work being done, that there is heat being dissipated, that there is free energy being expended. Those are all kind of related, interesting concepts associated with a non-equilibrium steady state, like the one we're talking about here. And again, just to reiterate what the point of this whole exercise is, it's not that I wanted to have a little love affair with phosphorylation-dephosphorylation reactions, although that's true. I mean, I think this is an amazing fact. I love the paper from Jeremy Guno-Ordena, where he talks about the use of post-translational modifications to escape genetic imprisonment. And phosphorylation-dephosphorylation reactions are one way to escape genetic imprisonment. In fact, earlier in the term, I gave a homework problem in which the students were asked to compute the number of different phosphostates of a single protein. It's a lot. You know, there might be 20 sites of phosphorylation. And so, you know, that tells you there's 2 to the 20th possible states of phosphorylation. If I have 3 million proteins in an E. coli cell, you know, it's an astronomically huge number of possible phosphostates, even in a single cell. So this phosphorylation-dephosphorylation thing is really interesting. It touches on the notion of allostery, which I've described a little bit, in the sense that phosphorylation and dephosphorylation can change the activity of some protein. It might be inactive in the absence of phosphate group, it might become active in the presence of that phosphate. And this costs energy. And so what we want to do is we want to have an assessment of the energy cost associated with those biochemical processes. I wanted to say a little bit about Carnot. So Sadi Carnot, in the mid-1830 or so, wrote this paper called on the motive power of fire. And the reason I bring this up is that I think it's very important for us all to think of the different versions of motive power. You know, that's in a way what he meant in the context of a temperature difference. What I'm saying is, you know, if I have a pressure difference, I can harvest that pressure difference to do work. I could have a container, I could have a wall in the middle, the pressure on one side is greater than the other. I have the brakes on that wall, and then I've shown you this earlier, I release the brakes, that wall is on wheels, and the wall, because of the pressure difference, is going to move, and as it does, it could lift a weight. So there is a motive power of pressure. Carnot, in this paper, notes that there is a motive power of temperature. If I have a temperature difference, I can harvest that in order to do work. And that's the nature of the Carnot cycle that you see in the bottom right here. And it's the basis of a great variety of heat engines. In the upper left, you see sort of the classic steam engine designs from the 19th century. The middle figure is a World War II vintage piston engine that drives propellers. And then on the bottom is a modern turbofan from a jet that I can fly around now. And my point is that, yes, that's cool. There's a motive power of fire. There's a motive power of pressure. But for us, when we contemplate biology, I think that part of physics is a little bit of a ripoff. And I say this often because I feel, you know, in my thermodynamic training, that there was undue importance attached to temperature and pressure in comparison with the importance of the chemical potential, which is another kind of motive power. I think it was Onsager who, you know, talked about chemical driving forces, like the chemical motive forces. And that's the thing that we're focusing on here. That's the reason for this whole exercise, this whole example. Yes, I love phosphorylation, dephosphorylation reactions, but what I'm really trying to do here is I'm trying to harken back to this idea of the biological battery, which we've already introduced earlier, and to note, you know, there's many different kinds of batteries. There's many kinds of motive forces. There's now, we're thinking about the chemical motive force, shown here, of ATP hydrolysis. We earlier talked about the proton motive force, the chemical potential difference, a gradient across the membrane. There's even a motive force, you know, that's another kind of motive force associated with the bonds in a sugar molecule. So combustion there allows us to harvest that. So that's what we're up to. Just to reiterate, we're up to now asking the question of what is the free energy cost per cyclic reaction, and then what's the total rate of heat dissipation or free energy consumption in order to drive these processes. Okay, so that's kind of where we are. So the goal then is to compute, loosely speaking, dF by dt, free energy usage, or free energy consumption rate. You'll remember that reaction 1 from our previous discussion was enzyme plus ATP goes to E star, phosphorylated state, plus an ADP. So that was reaction number 1. Reaction number 2 was the one where E star was converted back into E plus phosphate. And that has a rate K2, and the back reaction has a rate K minus 2. And I also want to note that J net on reaction 1, we said was equal to K1 times C ATP times E minus K minus 1 C ADP times E star. So this is the net. And I'm going to refer to this, we already did yesterday, as J1. And refer to this piece as J minus 1. And similarly, we had J net on reaction 2, and these are equal. They need to be equal to each other. So I have K2 times E star. That's what we refer to as J2. And then minus K minus 2 CP times E. And this guy is J minus 2. Just to highlight and remind us of what the net fluxes are that are passing through these reactions. And as I said a moment ago, these two guys are equal. And the reason is because we are indeed in an unequilibrium steady state. So we're just traveling around this loop cyclically, and every single reaction costs us a certain amount. So how much does one reaction cost? Well, I'm going to write it this way. One cycle, delta G, is going to be equal to mu ATP minus mu ADP, and then minus mu P. This is the part for reaction 1, and this is the part for reaction 2. What do I mean by that? Why am I making this apparently complicated and obscure? Well, let's go back to the diagram of the reaction. So in reaction 1, note what happens. I will circle it up here. Here is reaction 1. So we take an ATP, we take the enzyme, we go down this reaction pathway, and when we're done, we have an E star with a phosphate group attached, and we have left behind an ADP. So the pumps that are going to be invoked in this case are the ATP pump, which is going to bring in one more ATP because I've consumed one of them, and it's going to kick out one ADP. So that's the way I want us to be thinking about this. So that's the first bit, and that corresponds to the ATP, ADP, and so that part, if I think about this first reaction, that's going to be mu ATP minus mu ADP. Why do I say that? Because the reason for the plus sign with the mu ATP, remember mu is free energy n plus 1 minus free energy of n. And what we've done, the final state has one more ATP. So that means that the relevant quantity is the chemical potential. ADP went from having n to n minus 1. So the final state has fewer than the initial state. That means it's minus the chemical potential. It's telling us about the free energy cost for that one contribution. And so now on the second reaction, on this back reaction, what's going to happen is we're going to actually liberate a phosphate, as you see here. And so the net result is that in that reaction is we have to pump out one phosphate. And that corresponds to mu ATP, sorry, to mu phosphate. So let's try to now reckon that. So I recall that these things can be written as epsilon ATP plus KBT log of CATP over C naught, and then a minus epsilon ADP minus KBT log CADP over C naught. And then I have finally a minus epsilon P minus KBT log CP over C naught. I can reassemble all of that as EATP minus EADP minus EP, and then plus KBT log of CATP C naught over CADP CP. So that's the free energy cost of one cycle of this phosphorylation dephosphorylation reaction, one cycle. Note that, just remind yourself that this thing is the drive. In equilibrium, excuse me, in equilibrium, this thing is zero. Okay? In equilibrium, let's just note, in equilibrium, delta G for one cycle is equal to zero. And that tells me that delta epsilon, which I'm going to say is EATP minus EADP minus epsilon P is equal, say, plus KBT log CATP eq C0 CADP eq CP eq. This is hold on, I was a little sloppy. Sorry, I was just trying to define this as delta epsilon. This whole thing is equal to zero. And so what I've learned is that delta G, one cycle, I can now rewrite this. It's equal to delta epsilon plus this KBT log CATP, C naught, CADP, and CP. Because of this previous line, this is equal to minus KBT log CATP eq C0 CADP eq CP eq, and then plus KBT log of CATP C naught CADP CP. But what, you might be saying to yourself, what the heck are you doing? Okay, so what I'm trying to do is I'm trying to show you, I'm trying to rewrite the driving force, essentially, or said differently, the hydrolysis energy per cycle. I'm trying to rewrite that in some sort of a convenient and clean format. The first thing I did was I eliminated this parameter delta epsilon, which is the same as epsilon ATP, epsilon minus epsilon ADP minus epsilon P. The way I eliminated it is by knowing that in equilibrium, the delta G of one cycle is zero. That allowed me to solve this. I'm saying this thing is equal to zero. And so I used that to solve for, sorry, this thing is zero. That allowed me to solve for delta epsilon. I then substitute that in here, and that leads me to this condition. Okay, now I want to invoke one other thing that's interesting from earlier. So notice what we said in previous vignette was that in general, in the case of equilibrium, so I should have put the equilibrium symbols here. In the case of equilibrium, I have that the ratios of the concentrations can be rewritten in terms of the ratios of the products of the rate constants. So that's the thing that I'm going to invoke now. Okay, so let's rewrite this one last time. So we have KBT and then log CATP, C0, CADP, CP times CADP eq CP eq over CATP eq C0. C0s cancel, and I invoke the fact, which we just saw, that I can write this object as this object. Okay, so we're almost done. I hope the reasoning is not too tortured. So I finally have KBT log, and then K1, K2, CATP over K minus 1, K minus 2, CADP, CP. So this is delta G one cycle. I've performed surgery, basically. I found a way to rewrite the delta G for one cycle. And now I'm going to make an observation. I'm going to note something of interest. The observation is that this actually can be rewritten as KBT log of J1, J2 over J minus 1, J minus 2. How do I know that? Notice what I wrote up here. I defined these four quantities. So if I have, note that I have K1 CATP here, that's J1. Here's K2, so J1 is this bit, J2 is this bit. And if I take the product of those, I get K1, K2, CATP, E star. Okay, that E star is not in our final result, but you're going to see it's going to cancel out. In the denominator, I have this object times this object. And what I'm left with when I construct those ratios is precisely what I have written down right here. This guy is equivalent to this guy. Okay, so that's pretty cool. What we've done is we found that this very interesting result, which is that the delta G in one cycle is given by KBT times the log of the products of the forward fluxes divided by the products of the backwards fluxes through this cycle. Last comment I want to make is that dF by dt. So now let's say we're interested in the rate. Well, that's, as we've shown earlier, is going to be given by J net times delta G one cycle. Right? In other words, this part, delta G, this tells me the energy of free energy cost per one reaction. And this part tells me how many reactions per second. So the net result is the free energy per second. That's the upshot of this. I'm going to make one more observation, I'm going to stop. So this is all, so I could, by the way, rewrite this as J1 minus J minus 1 times log of J1, J2 over J minus 1, J minus 2. And rewrite that further as J1 minus J minus 1 log of J1 over J1, my J minus 1, I mean, plus, oh man, I need my KBT. Sorry, I'm getting a bit sloppy. It's kind of early in the morning and I'm rushing. Plus KBT, and then J2 minus J minus 2 log of J2 over J minus 2. This is equivalent. How do I pull that off? I pulled it off by noting that J nets are equal. So, first thing I did is I decomposed this log of J1 over J minus 1, J2 over J minus 2 into a product, or sorry, a sum of these two logs. And then I just noted, well, J1 minus J minus 1 and J2 minus J minus 2, because this thing is in a non-equilibrium steady state, those are both the same. And this is, a specific example of the more general, I want to say more generally, I have that dF by dt is going to be given by sum over I and j of ji minus jj log ji over jj. Something like that. I need to put a KBT again. So we've basically written down a specific example of this more general relationship. So what did I want you to get out of this? I mean, let's go back to our diagram of the reaction that we've been thinking about. So in sum, what I tried to tell you was, first of all, that the ATP battery is, as I keep iterating or reiterating, is like the plug in my wall right there. I keep on saying that because it's true, in the sense that I have a universal currency which I can draw upon to do many different parasitic reactions, charging my iPad, charging my computer, which is what I'm on right now. I'm just holding it up. The light that you see over behind me, the charger of my hard disk, etc. There's just all these things that are parasitic off of the plug. So I have this ATP battery. We worked out just now, that the free energy available per cycle from that battery is given by this simple result. And the way that we're thinking about that is that we're representing the battery in terms of three reservoirs. We have an ATP reservoir, an ADP reservoir, and a phosphate reservoir. And what we're doing is that every time we undergo one of these reactions, we're performing pumping operations where we're pumping in ATPs and pumping out ADPs and phosphates. And the net result of that is this cost. And then what I invoked was, essentially the second law of thermodynamics, which is, some sort of a statement about dF to T is equal to J net times delta mu, and that's that the cost is greater than or equal to 0. We also had worked out, the steady state fluxes, because this thing is in a non-equilibrium steady state. So, that's the sum total of what I want to say by way of introduction. I think, I'll try to write up a homework problem that really causes people to, rather than just watching me go through the motions, requires the students to look at each step of the logic that I just went through carefully, because the logic is a little bit, I don't think it's convoluted, but there are a couple of subtleties, like just to at least report on what I think is subtle. One of the things is to just keep reminding people, because I think we don't have this comfort with chemical potential like we do with temperature and pressure. If I tell you that there's a pressure gradient, it doesn't surprise you if I say that the pressure pushes on a piston, that the piston will move. You're used to that, and that movement can be used to do work. And so I'm just trying to say, that there's all these different kinds of drives where there's a free energy associated with a degree of disequilibrium. I have disequilibrium in pressures, and I can harvest that. I've already said that. If I have disequilibrium in average energy, which is another way of saying temperature on two sides, then I can harvest that also to do work. But if I have different chemical species and they have not attained their equilibrium, I can actually use that to do work, to lift weights, to literally lift weights, as long as I can construct the proper coupling. That's I keep on making this point about coupling, that what we want to do in a way is produce AND gates where some reaction that we're interested in making happen can only happen when it's tied to ATP hydrolysis. And I got to make sure that the ATP hydrolysis wants to happen to be anthropomorphic, because the ATP-ADP ratio is out of equilibrium, which means that this drive is non-zero. So anyway, we used equilibrium here to solve for this delta epsilon, and it led us to this very nice result that I've shown here. To me, this is really the essence of it, is that the free energy liberated, free energy used, I should really say, per cyclic reaction can be written in this very special form, which ends up being the products of the forward fluxes divided by the products of the backward fluxes. Very general thinking. So I think that's what I wanted to say about phosphorylation, dephosphorylation. I think that for this year ends what I wanted to say. Well, it doesn't end what I wanted to say, but it ends what I'm going to say about life as defiance, about the way that energy is paid to do so much of biology. I realize that I've talked a lot about equilibrium and non-equilibrium. I have a rather harsh response to those who just dismiss out of hand the use of equilibrium ideas. The use of equilibrium ideas is very solid, even in non-equilibrium settings. And in those cases where we need to stop it, I've shown you that. I've tried to give a sense of what non-equilibrium steady states are, but I want you to notice that we were able to use the language of free energies, even though we were not talking about equilibrium. I used this kinetics, dN by dt is equal to minus gamma times dF by dN, where F is a free energy. That F, it exists in a state where the system is not in equilibrium. And the simplest version of that, which we did a number of times, but I just want to, I want to remind you of it. The simplest version of it is we just over and over again invoke this idea of a little system separated from the world by a wall that is adiabatic, it's rigid, it's impermeable. So this is my wall on the outside. And then inside I have system 1 and system 2. And, I might have more molecules over here than over here. And so if I make a little opening in the wall, right here, if I open up the wall right here, because there's a chemical potential gradient, there will be mass transport. I can describe that in terms of the free energy. There's the free energy, which is a continuous function of the number of particles on the left, which can run from 0 to m2. We wrote that free energy down. I gave it as a homework. So there's a free energy defined everywhere along that pathway, but only when the chemical potentials are equal is that thing in equilibrium. It's just to say, that in this field, in materials physics, when people write down descriptions of coarsening, of microstructural evolution, and so on, they do exactly the same thing. They write down a dynamics of the form d something by dt is equal to minus a kinetic coefficient times d free energy with respect to something. It's a very standard thing. I mentioned it earlier as Model A. I showed you the page from this book, this great book by Mayron Carter. I showed you page, which I think was 192. I'm not sure, but where he tells us, we're we're basically kind of generalizing Langevin dynamics. Yeah, page 192. So this is the page where he talks about the Langevin equation, and that's the df by dn dynamics that we've been writing down. Okay, I don't mean to be so long-winded, but I do feel that I have been confused over the years about these matters, and I feel like when I talk to people, there's a lot of confusion. My hope was, in the words of John Wyndham, to have shedded light rather than darkness on this subject, and the light that I wanted to shed was this notion of biological batteries, the idea that lots of biological stuff requires drive. You can use the different kinds of drives. We showed the symporter example as one kind of drive, where the drive there was the gradient across a membrane. So we had basically a transmembrane chemical potential difference. And then this time we talked about invoking a different biological battery, which is ATP. We used the case of phosphorylation-dephosphorylation, a ubiquitous and very important example of post-translational modification, to illustrate the general principles of how ATP hydrolysis gets harnessed. I hope you enjoyed this part of the course. What we're going to do next, and we'll end the course, is talk about signaling, regulation, feedback, and control. How it is that signals lead to regulated behavior of transcription and so on within cells, and the important notion of feedback that leads to behavior such as switches and oscillators and so on. morning and welcome back to the course. We're in the middle of talking about phosphorylation-dephosphorylation reactions. We're using this ubiquitous biochemical process